In this presentation, I would like to speak about the results, our recent results on an experimental investigation we did on the effect of realization parameters on the curvature ability for the textile. And I will do this by first briefly describe our interest in such field and the aim of our work. Then I will present the material and systems we have investigated and finally show the most relevant results for two specific geometries and also add some consideration or preliminary consideration on the adhesion it can be achieved in these systems. So I don't think there's need to define what is 4D textiles after this beautiful opening talk by Professor Gries, and I will just limit to tell you what I find particularly inspiring in these innovative smart systems, which covers aspects that are related to technologies. Simply put, it is possible to obtain very complex 3D structures starting for simpler 2D patterns, but Professor Gries showed us that the technology may be even get to more challenging aspects and functional aspects, since the structure that we may obtain are self-assembling, relatively compliant, they may be thin and light, and they may be also provided with stimuli responsiveness. And finally, I would also say that the easy realization of these systems may be particularly helpful also for teaching and disseminating the concept of 4D printing in workshop, in lab session, or team events. On the mechanical side, however, the 4D textile behavior may be summarized as a complex response from these three features. We have a structure that rapidly changes its shapes as tension is released, and the driving force is typically a biaxial state of stress, and the obtained shape is dictated by a mechanical equilibrium between the stretched textile and the printed elements. And this in turns depends on various parameters, which are the properties of the constituents for the textiles, the textile pre-stretch, and the geometry of the printed pattern. So the aim of our work was just to experimentally investigate the complexity of this response, as well as to find out some correlation parameters between realization parameters and the complex obtained curvature. So the 4D textile we have investigated were prepared really starting from commercial material, and highly stretchable, knit lycra textiles, and the PLA filament that is suitable for FDM printing, so very basic. And the structural morphology of both materials is per se complex because they are have an anisotropic behavior. However, in the case of the textile, this is particularly relevant above 60% strain, which were not explored here. So the main difference between the two, or the main, let's say, relevant consideration on the mechanical side regards the stiffness mismatch between the textile and the polymer, which may be quantified around about 3 orders of magnitude. The constituents were assembled by first subjecting the textile to a nearly homogeneous biaxial stretch by mounting it on a rigid frame, and this was done at various pre-stretch levels up to 60%. And then the textiles were used as a layer on which, under standard pre-optimized printing condition, 2 different patterns were printed. And concerning the geometries I'm going to show you, we had carried out some preliminary experiments, which consisted simply in printing bar-shaped elements with various thicknesses and width on pre-stretched textiles. And the results clearly showed that the obtained curvature was significantly influenced both by the presence of the textile contour around the printed area and by the specimen, by the printed area width. And this suggested that beside the stress at the textile printing element interface, also the stress that is accumulated in the surrounding area has an important role. So for this reason, two specific geometries were investigated, a single 8-arm star structure and a multiple 3-arm star pattern. And this was done in order to take advantage and to convey a large portion of stretch textile surrounding the printed areas in order to have the morphing effect. Both structures were realized for various levels of the PLA thickness and the textile and of the textile pre-stretch. In addition, for the 3-arm star structure pattern, also the mutual interdistance of the repeating element was varied in order to control the final shape. So I'll start with the 8-arm structure. And as you can see, as the stretch is released, the structure typically assumes a dome-like shape, as shown in the picture and in the 3D scans. And we also try to evaluate, by means of digital image correlation, the strain upon the stretch release, which actually show that during the shape shifting, two values of strains originates. The printed structure deflects with no axial displacement, while the region between the printed area undergoes significant contraction, helping the achievement of the dome-like shape. And we speak about the dome-like shape, but actually by changing the parameter, it is possible to obtain various types of figures. And of course, as expected, larger curvatures are obtained for lower thickness and larger pre-stretch. But by looking at these figures, we can see that these two parameters lead to a very wide range of equilibrium shapes, which ranges from the degenerate case of no curvature, which is obtained for low pre-stretch or large thickness, to curvatures that are almost self-wrapped shape for high pre-stretch and low thickness. And only intermediate values of the parameters or combination of the parameters led to more regular dome-like shapes. We also try to evaluate the curvature by measuring the change in the overall projected area of the dome and the height of the dome as a function of the pre-stretch, and find a regular dependence for each values of thickness. Only in the case of the thickest system, the curvature was completely hindered. However, for this system, or for even higher thicknesses, it was still possible to activate the transformation in a curved surface by thermal stimulus. And this was done because by heating PLA above its glass transition temperature, a significant reduction of the PLA stiffness to value of about a few megapascal changes the equilibrium condition between the textile and the PLA and activates the shape shifting. And so interestingly, the material does not change its shape until the transformation temperature is approached and undergoes a change typically in 10 to 30 seconds. And this suggests the possibility to store the printed system material in a flat configuration and activate the shape changes by a highly specific thermal trigger, somehow like the pasta we saw before. So the area reduction and height increase is shown for various pre-stretch and PLA thickness. And the results actually suggest that a more important effect is given by the pre-stretch with respect to that of thickness. And in the case of the 3-arm star-like patterns, we found similar result. The overall printed area undergoes a dome-like curvature, as shown in the picture in the 3D scans, and the state of strain revealed by means of the digital image correlation shows a diffuse region of strain among the elements. However, in this case, a more complex scenario is displayed for the curvatures that may be described in terms of 4 types of appearance. The flat degenerate case for the highest thickness and the minimum strain. In yellow, a region in which the overall curvature is provided by cooperative action amongst the various elements. In green, another region in which the curvature occurs but regards only the single elements in a non-cooperative manner. And finally, for the highest stretch and the minimum thickness, a region in which both the cooperative effect and the single curvature takes place, almost with some self-wrapping in the end. And by changing the mutual distance, it was possible to greatly tune the extent of region of cooperative and non-cooperative curvature. And as expected, when the elements are close, the cooperative effect and as well as the double curvature are more dominant, are more likely, whereas when the elements are far, the non-cooperative curvature of the single element is more typical response. And we also measured the array shrinkage for the various systems and the 8 increase. They are similar to what we have found out for the 8 star, just a little bit more complex for the various type of interdistance between the elements because of the different shape-shifting scenarios that may be activated in the various cases. Just before conclusion, I'd like to show that we also are considering the problem of adhesion between the printed layers and the textile support, and we try to measure in 90 degrees TPL tests along the principal direction and for all the applied pre-stretches. The elements, as you can see, the curve shows a very high local nature of the delamination failure, so that the sample could feature zones of high adhesion close to region where the adhesion was poor. And just to provide the value of maximum adhesion, we averaged the highest time peak, and the results are reported here along with the curves. At the first glance, it seems that the results are quite scattered for all the behavior, and I will say that there is no such drastic difference between the PLA surface in contact with the textile. And in addition, despite the highly distributed strength values, all the specimens revealed sufficient adhesion to maintain the elements connected during shape transformation. However, as you can see, it is suggested a larger pretension, probably because the polymer gets better in the textile, and for some specific direction seems to statistically present higher peaks of adhesion. However, further tests, in particular an adjustment of the printing parameters, are currently planned in order to provide both better understanding and control of the interfacial strength. And so I like to go to the conclusions, saying that we have carried out this experimental investigation with the correlation between the realization parameters and for the textile response. For what regards the complexity or the peculiarities of the shape evolution, we can see that this is strongly affected by the stress in the region that surrounded the printed area, and that realization parameters dictate not only the overall curvature, but also different type of curvature. And for what regards the effect of the realization parameter, beside the obvious higher curvature for high pre-stretch or for thinner printed elements, we see that the regular shapes may be assumed only by specific combination of pre-stretching, thickness, and interdistance, and also that thickness may be used as a way to temporarily fix the material in a flat shape and to activate in a second moment the shape shifting above the glass transition temperature. And as I told you, current investigations are now carried out in order to control the adhesion. So thank you for your attention.